Christopher Spirito. Christopher Spirito is a nuclear cybersecurity consultant, Idaho National Laboratory. Hacker Sanctum Security. Chris believes technology should improve people, not control them. As founder of Sanctum Security, he crafts liberation patterns, workflow optimization designed with uncompromising precision, elegant simplicity, and intentional design, making sophisticated security accessible without deep expertise. Currently, a nuclear cybersecurity consultant at Idaho National Laboratory and support U.S. partner program and service as a PI for research on FPGAs and autonomous operations in advanced reactors. Previously, he was the international cyber lead for the Mitre Corporation, leading global cybersecurity initiatives, and has served on the board of Wired International for 15 years, delivering medical education to undeserved communities worldwide, embodying his conviction that whether through security or health, technology must empower human dignity and potential. Thank you, Chris, for your join to our conference, and welcome for your presentation, Chris. Welcome.
Thank you. I appreciate you having me today. So how much time do I have? I want to make sure I keep your conference on schedule.
What you would like. Sorry for some delays.
No.
You saw which very interesting discussion in previous our presenter has said 30-40 minutes. I think it's okay. Welcome.
Perfect. Yeah, I'll plan for 30 minutes, and I definitely appreciate being able to give this talk right after the talk on syphilis surveillance, right? Because as you noted in the intro, the work that we do in global health for Wired International actually has a fairly interesting surveillance component to it. So any sort of advances in the field of epidemiology and healthcare surveillance is pretty helpful for us to understand how we can apply that to our global health practice. So that was a very good talk that we just listened to. So let me go into full screen mode. I'll plan for 30 minutes, and then we can do some questions and answer from there. So I'm going to put this into full screen right here. Okay, and continue to share. And hopefully you're still seeing everything. If not, just say something, because I can't see the panel of attendees anymore until I finish the talk. Okay, so today what I wanted to talk to you about was this concept of supply chain risk analysis. I call it from chip to chain reaction, sort of as a nod to the work that we do in nuclear energy. So first and foremost, let's just sort of consider the phone that you're holding in your hand, right? And so I first gave this talk in Jordan a couple months ago, which is why you see the country of Jordan highlighted on the map. And you'll see the website of the conference on the phone there. Now, when we purchase a phone, when we acquire a phone, we sort of order it or we pick it up from a store, and it sort of arrives at our house or in our hand, and we make a lot of assumptions regarding the electronics, microelectronics, the software stack, the hardware stack, the driver stack inside of that particular component. And one of the things that we're always sort of wondering is, hey, where did this phone sort of originate? Where did all the components come from? That's sort of our core supply chain analysis challenge. And so from that, we jump back a little bit. So let's go back in the supply chain a bit to China, right? So if you've purchased an iPhone, it's likely that your phone originated from some factory in China, in Shenzhen. And, that's where the assembly took place. And, what you can see there is you take the back off a phone and you see all the different components, from both the integrated circuits to all of the different integrated components themselves, from the cameras to the ports to the motion sensors to everything that's used inside the particular phone. And each of those has an associated set of sort of capability stacks to it our concern, of course, is at the component level, like, hey, did they install something that was meeting the design specifications? And if so, was there any additional features that were included that sort of were, sort of not expected, if you will? So we're trying to defend against those, implants. We go back a little further and we might end up in Taiwan, right? Where now, further down the supply chain, you have these chips that are, manufactured in the different fab facilities. And again, you put together your design, you design the chip based upon the, capabilities you need for that particular, chip over time. And so when you look at the processor timelines or the component timelines or sort of cycles, you see the evolution of these components over time, and you see that we're now packing more and more capabilities into these smaller and smaller, chips, and therefore it presents, even more challenging, surface for us to perform an analysis on. And that's really the crux of this presentation, is how do we perform analysis upon these layers and layers of what I'll call attack surface or defense surface, if you will. So let's just say that, the chip manufacturing takes place, but on the way to China, the chip stops by perhaps a country that doesn't have everyone's best interests, in hand. And in this country, at the microelectronic level, there is some sort of modification made to the chip itself. And so now the chip that you thought was, this particular set of capabilities now includes either altered capabilities or additional capabilities that you are now responsible as a cyber defender from figuring out, like, hey, could these things exist in the system? And if so, how do I make sure that I don't deploy these two critical systems or safety systems, in this case, in the nuclear sense? And so as the journey progresses around from the Taiwan and the chip manufacturers to Shenzhen compiling things together, assuming there's sort of, a stop along the way, we do end up with a little bit of a technical challenge in analyzing this attack surface. So from this, we go back to our site in Jordan, in this case, and the question ultimately becomes, hey, what do we do about analyzing layers upon layers of attack surface? And because those chips don't always go into phones, right? They don't always go into devices that, are not necessarily critical devices. They do end up in instrumentation and control systems that run different parts of nuclear power plants, different parts of energy systems. And from that, we need to be able to make sure that as we identify the critical functions and the critical systems within our environments, we have a mechanism for being able to assess them. So based upon that, we've come up with a sort of an interesting approach to how to accomplish this. Inside our world, we have this view that we call the perception comprehension loop. And I think on this sort of conference, everyone is a scientist. So this is the daily process that you engage in, right? You set of hypotheses up that you believe, might be, testable. You put some constraints around the hypothesis testing, and then you perform some analysis in order to be able to understand whether you can validate or nullify that particular hypothesis. So we have our perception of what we believe to be the sort of component or attack surface or whatever it might be, but then we actually have the comprehension after analysis of what it actually means. And this is important because we're now looking at these surfaces that have 10 to 20 billion transistors per chips and hundreds of manufacturing steps. I just showed you a few, but really you have hundreds of manufacturing steps along the way that are dependent upon these global supply chains of the components coming from multiple countries all into single factories for putting the components together. All of those supply chains have vendors and sub-vendors that have to be managed. And therefore, we do end up with millions of events that are we able to analyze if we can gain access to all those events, which do help us perform that kind of similar surveillance function across the supply chain, should there be some sort of threat on subversion of the supply chain of the components that will ultimately make their way into our critical system. So this is the challenge that we're looking at. And it's going to run from the chip to the component, to the system of systems, to the facility level. So we have an opportunity to perform this analysis every single step of the way. And so from that, what we ended up putting together is these analysis patterns, right? So if you've spent any amount of time in software engineering, you've encountered software patterns, right? So when we have a particular problem that we're trying to work, we look for a pattern that has been known to be able to approach the solvability of that problem, in production, right? So if we have a queuing problem, let's say we have, tens of thousands of events that are arriving, per second, we need a mechanism for being able to move those through a queue efficiently. We have to understand how we can implement those across load balancing queues, across load balancing processors, and then, of course, understanding the actual physical requirements of that data moving across the physical devices. And so in a similar way, we've come up with some analysis patterns that we use in order to perform this, attack surface analysis, at every single layer. And so the patterns are all structured with these 5 essential components, which is a workflow challenge, or what are we trying to achieve? What's the framework implementation? How are we going to implement that hypothesis testing in order to be able to gather the evidence, in order to answer our questions? We implement a cost implement function against this, so we can actually figure out, based upon the number of digital assets we have, which again, in some facilities, you might have tens of thousands of digital assets. What is our cost to implement, and how are we going to do our statistical sampling of the target environment in order to determine which of the systems we should be performing analysis against? We have our runtime interpretation and tuning, which is essentially an opportunity to take the data that we have received during the analysis process and be able to perform additional, sort of findings analysis on it. And then that determines how we can share that with other teams performing similar types of analysis. And then for the output, the sector guidance, right? And so our main interest is in nuclear, but of course, there's sector guidance related to this analysis is applicable across pretty much, every sector that includes microelectronics. And so starting off with our workflow challenge for silicon analysis pattern, and this is the engineering teams receive gigabytes of chip test data, but they ultimately lack the expertise to identify these subtle anomalies that indicate vulnerabilities. Now, the one thing that is interesting with regards to test and evaluation of, components is that every single defender sort of has their boundary point of knowledge, right? So when you first start performing analysis on, target systems, you might start at the operating system level or the application level, right? So let's just say that you are someone who's performing an analysis of, let's say, a website exploit, right? What you might actually choose to do in that case is start with the network capture, and the network capture will then allow you to see the data packets that are moving through. But then you might say, well, as the data moves down the stack, I need to look at the IP stack, driver. As the IP stack driver actually interfaces with the hardware, I can look at the Ethernet hardware driver implementation, and I can keep on working my way down layer per layer. But ultimately, as a defender, we actually have, sort of initially a boundary of knowledge that comes to analysis of the target space. Our goal here is to be able to try to have, cyber defenders who are not as sort of competent and capable with the lower level analysis, or maybe don't even have the hardware that would be necessary to perform this analysis, be able to take steps towards understanding that particular attack space. So the workflow challenge again here is, I might not have the, sort of hardware that I need to perform, delayering of chips, but I do have access to, chip data, right? So I can request from my, vendor some additional data regarding the chip. So something simple with an IoT device like an STM32, microprocessor, or something more challenging, right? Like an M2, M3 from the Apple chain. You obviously have some test data you can work against. We take those test files, we take those data sheets, we take those risk parameters, and then we put them into essentially generic LLM, implementations, right? So, for example, we here utilizing, the GPT-5 for pattern analysis against those particular targets. And then we can use any of the Anthropic models performing explanations of what's being identified. So we have model diversity in this particular analysis pattern. We have a broad enough training data set that allows us to work against those particular types of targets. And we end up with some fairly interesting information that are moving out of the model analysis when we input the test files and data sheets and risk parameters. We perform validation of this using some rule-based and confidence scoring validation, largely based upon our past actual hardware analysis. So the one thing I should say here is that this isn't simply an LLM, sort of implementation. This is actually an implementation that's leveraging LLMs, but based upon our past actual experience of analyzing hardware. So it's hardware-informed analysis, which allows us to do more sort of appropriate structured querying against the LLM in order to determine what we want to find from the data that we're importing into it. Our outputs end up being risk reports, vendor questions. This is really important for the sites we work with that don't necessarily have, again, that knowledge of what to ask a vendor about supply chain risk. So in this case, we can say if you're acquiring this particular type of chip inside this particular type of component, inside this kind of system, here are the types of questions based upon the analysis of the data that we just performed that you should be asking to the vendor in order to ensure that you have a, sort of a good feeling about their handling of their supply chain as that component flowed down to your environment. We produce some intelligence products from that. We have confidence scores, anomaly explanations, vendor questions from there, and then some attack surface enrichment, and then some supply chain risk management indicators. Now, the indicator part is really important, especially if you're architecting a new environment, right? So sometimes we'll work with, sort of a partner, and the partner is implementing, let's say, a new distributed control system, right? So they're building out a new DCS, and that DCS once operational, is going to be a little bit challenging to inject new capabilities into. We talk to them about what do you want to include for indicators of supply chain risk compromise now, such that when the system is operational, we'll have access to that data, because once the system's operational, we're not going to have the ability to change the configuration such that we can collect that information. So this type of analysis is both good for supply chain risk analysis, but also for being able to pull out those types of indicators so we can actually configure the sensors inside the environment to collect the data. Okay. Generally, we've identified this to be about a $2 to $8 per chip cost based upon the number of tokens that we need to submit to the different LLMs in order to perform the analysis. The time to analyze is not, too much, 5 to 15 minutes generally, depending upon the amount of data that's inputted, but also really the type of patterns we're implementing for the deep dives. Runtime and interpretation and tuning. So now we take our confidence thresholds, we loop those in through our human review, and therefore we end up with this essentially multimodal model consensus for these critical findings, output in structured format. So that way these can be ingested by the other patterns that we use. And the other patterns we use, you'll see at the bottom of the chart right here, include things like data translation patterns. So we heard in the previous talk, about the syphilis surveillance, the ability to perform that particular data curation. That's one of our largest problems, right? Is that we have lots of unstructured or semi-structured data. Being able to take that data and put it into some sort of form that's usable within a questioning framework is a little bit of a challenge sometimes. So we want to make sure that we take the output of the silicon analysis pattern and be able to ensure that it can be ingested into other patterns in a structured way, so it doesn't become too much of a headache for the scientists from that analysis. We have intelligence routing patterns, which essentially just indicate dependencies between the analysis patterns we're using. Correlation patterns, which essentially is things that I know exist in multiple domains, how they relate together, and whether we can then perform statistical analysis of correlation causation in those particular domains, and then handoff validation patterns of how to move this between organizations performing similar types of pattern analysis. So that's sort of a rundown on one of full chip level pattern. But from there, we have patterns at every single level. So if we go from the chip level to the component level, now we have a little bit of a different, workflow challenge. So in this case, our acquisition teams must verify component authenticity, for example, across global supply chains, but again, often lack tools to trace provenance through vendors and detect counterfeits here. So we'll take, again, a similar type of inputs from component documentation, vendor information. We'll take the data from our chip pattern that we just used, if we have available to us, and put that in, but also some additional chip data. And again, we can use, GPT-5 for provenance analysis. We can use Claude for anomaly detection. And then we can actually produce some sort of, basic blockchain that allows us to have digital signatures and chain of custody across the different components that we're ingesting, which will help us in the future when we get notified of some sort of vulnerability, so we can actually be able to take that data and trace it through our entire digital infrastructure to identify which components might likely be essentially affected by the announcement that we saw with regards to the vulnerability. The output here is going to be risk reports, vendor questions again. We'll have some component authentication that we can actually then feed back to the vendor if it doesn't exist, to say we would like to be able to implement this in existing or future versions. Vendor risk scoring, it's a little bit fluffy, if you will. takes a little more sort of cycle time in order to be able to really have a score that maps to a vendor's capability in the space. But also more importantly, I think, is vendor intelligence and then the bill of material validations that they send through. It's sort of a frequent observation that the bill of materials that you receive from a piece of hardware or software component doesn't always exactly match what you end up receiving. And so we need to be able to work the gap of why that is, if you will. Sort of a similar component implementation cost and timing. In this case, the runtime interpretation would include high-risk component triggering deep inspections. So in this case, as we see components like, again, safety systems in nuclear plants, safety systems pretty much in any industrial process are going to be the types of targets that we would call, high-risk components, or component systems that contain high-risk components, therefore would require deeper inspection. And that way we could essentially say, these are the systems that we want to perform this high-level analysis on. The other ones we can actually bound out and determine how to sort of analyze any sort of anomalies on those systems. And since we have time between the system being able to sort of produces the anomaly and the system actually faulting, if you will. Sector guidance here would be mandatory crypto verification and defense, focus on these safety critical authentication systems in automotive, and then industrial cost versus risk for high volume procurement. So you'll see the data translation patterns again, the blockchain validation patterns, correlation, then vendor risk scoring that comes out of this particular component level verification. Now, again, as we move up the stack, we now end up at the system level. So this one's a little bit different than the previous two. So the chip level and the component level, we were showing you what I would call fairly sort of predictable analysis, right? So at the chip level component, we're looking at those actual targets themselves. At the system level, obviously we're interested in the system, but we also have some additional sort of concerns at the system level. The first of which, let's say, is behavioral monitoring, because we are really concerned about insider threat inside these environments. So in this case, we have an operations team monitoring systems that are generating millions of events per day, but ultimately lacking expertise to distinguish normal operational variance from cyber effects or degradation versus an actual attack. Now, the one thing I will state here sort of very clearly is that this sounds like it's very approachable, but when you actually are working with operational data from operational environments, it turns out it's a very, very messy challenge to be able to distinguish that normal operational variance from cyber effects, simply because in very noisy environments, when you have lots of data, being able to essentially establish normal, what you consider normal data is not so sort of a trivial matter, but also the requirement for being able to determine variance in cyber effect is largely based upon your knowledge of what that variance would look like. You have to kind of know what an attack would look like in this environment, and you may not always understand what those attacks look like. And we're going to get to that in a second, how we approach that problem for those who are not as sort of well versed in cyber campaigns and effect delivery. So in this case, again, GPT-4 maybe for learning, Claude for explainability. We can use, in this case, time series clustering and drift detection models. These are very, very specific models that would be used because we're looking at time series data. So that's how that would play out. The behavioral baselines would be outputted plus probabilistic alerts. And again, we want to be able to take these during the architecture phase and be able to use these to sense up our environment to be able to then build this into production, so we're ready for when these sort of events take place, that we can respond to them and have our incident response team be able to look at that particular data. Cost to implement a little more expensive, simply because, as you know, at the system level, now we have to sort of work our way down through the component and chip level based upon the component system that we're analyzing. So it's going to be a larger cost, but also the system level analysis will want to be implemented, on a recurring basis. So in our world, we're always measuring thing in cycle times. Our cycle time is ultimately going to indicate our maturity level. So if we're able to implement, cycles that cycle shorter in order to perform the same sort of depth of analysis, then we're going to have a higher maturity level for a system implementation, because now we're able to perform a sort of more rapid introduction of sort of effect-based knowledge into the rule sets. So in this case, we'll have runtime interpretation and tuning of confidence thresholds for alerting, baseline drift detection, and integration with our SIEM and incident response workflows, the data moving out into the other business processes. Correlation patterns, time series, data translation, baseline drifts, and then as you can see, this would apply across the different sectors. Now, moving up one more layer to the system of systems layer, now we're actually moving up really into the event-based layer. So now you have security teams mapping attack vectors across these connected systems, but again, ultimately lacking some tools sometimes to enumerate those interactions, vulnerabilities, transitive trusts, and emergent attack pathways. Similar implementation here. Now we're taking architecture documentation, network topology, but now behavioral baselines from those system of systems analysis and be able to put those into our analysis and perform outputs that include attack surface maps, interaction vulnerabilities, transitive trust maps, and attack pathway enumeration. Now, as you might guess, attack pathway enumeration and interaction vulnerabilities are interrelated, right? Because cyber campaigns don't exist at a single point in time. They exist across multiple systems, across multiple components, across multiple chips, across sort of multiple minutes to hours to days to months. So we need to be able to analyze that particular attack pathway in a temporal, context in order to be able to determine what the jumps look like, and then that would actually give us some better ideas on that transitive trust maps and how we would be able to determine whether someone has, essentially implemented something on them sort of pretty thoughtful about, but it turns out it was not sort of the best choice in that moment. Cost to implement here, $500 to about $2,000. Again, this is going to be a continuous monitoring that you're going to perform on a monthly basis. So it's a little bit more expensive, but certainly less expensive than the incident response and the recovery that would take from an attack being successful inside the environment. Runtime interpretation and tuning, as you might guess, continuous monitoring allows us to move things into the cycle time faster, integrating this with our vulnerability management workflows and prioritization on the criticality and exploitability. And this is across different sectors. So now we've implemented graph analysis and attack tree patterns into our pattern library that supports this attack surface enumeration pattern. Now, how we actually approach the problem with regards to essentially partners who are not as well versed in attack surface, right? Or essentially attack methodologies. So we run a lot of, I guess there's two things here. One is we run a lot of sort of scenario development games. So we create these, sort of characters that might exist within a particular organization. And characters here will include things like, Riley Stone, the human firewall, and then Sam Kwan, the breaker of things, and Max Delgado, the curious cat. And they, each of them have a little bit of, if you ever played like Dungeons and Dragons or any role-playing games, they have some, sort of attributes associated to them with regards to intelligence and wisdom and charisma and dexterity. And, they actually have some sort of special skill, like, Riley has a gut check skill, is really sort of good at spotting tampering. And then, Sam Kwan has something called circuit sense, an advantage on physical system bypass. And then Dana Voss has the advantage of piecing things together. He's very, very competent at pattern analysis and pattern seeking. And so we create these cards, we put together these sort of big scenarios regarding taking the actual architectures in our environments and being able to come with a series of essentially attack pathways that would allow us to then determine, based upon these types of attacker profiles or defender profiles, what might be the digital systems we want to be able to focus on in order to be able to best protect our environment. So we combine this data with what you see on the right-hand side, which is something I called anti-pattern analysis. So we have all these patterns that we're using, right? Because they're sort of helpful for us to approach problem solving, but pattern implementations also assume that we make some assumptions on the usefulness of the pattern. And oftentimes we make assumptions that are not always going to hold in the operational environment. So the idea of anti-pattern analysis is to identify design choices that really seem reasonable, but ultimately create hidden vulnerabilities. So a good example would be the first one, which is a hierarchical function consolidation. So you might be in charge as the security engineer of being able to implement security for a set of, again, systems or systems and components or a system of systems together. You might then start listing out all the different functions that exist within these systems. You might start grouping them together in order to be able to apply a common set of security controls to those particular functions in your systems. And you might make some assumptions regarding the hierarchy of those functions in those groups to each other. Now, that's really good security engineering, but the issue might be is that your sort of reasonable approach to good security engineering ultimately may produce some vulnerabilities when implemented on the actual physical devices. And so we perform this anti-pattern analysis from things like hierarchical function consolidation, event drive function triggering, optimistic cascade terminations, spatial diversity without temporal analysis, incremental integration validation. These are all different, well-intended engineering principles that, if implemented not quite correctly, can often induce into the target environment types of vulnerabilities that a very sort of clever attacker would be able to identify and then exploit at a period of time of the sort of their choosing, if you will. So we combine this sort of story writing with this anti-pattern analysis in order to enrich the analysis that we perform across the system of systems. And then finally, moving up, we have this sort of facility level analysis. And this is where we're now going to do cross-layer risk assessments across all the different systems in our facility. So obviously the cost is going to go up because as we're doing facility level analysis, we now have again, tens of thousands of digital assets. We have to be able to choose which ones are going to be part of our assessment, cohort, and then be able to work against those particular systems. The output of this will be visibility and risk correlation across layers, cascading failure scenarios based upon some of the scenarios in our analysis, and then maybe a compliance dashboard if you can work out some indicators or values that you believe would be good to track over time, if you will. In our sector guidance here, nuclear safety system integrity validation. In defense, you might look at RMR or SRM prioritization, and then healthcare, maybe some privacy and patient safety risk. And so as you can see, we take all these patterns together, and it allows us to perform this sort of good supply chain risk across all the different layers. Now, the big reveal here, of course, is that chip that you saw at the beginning that went from Jordan, or actually started in Taiwan, and then goes to perhaps another country, and then goes for component assembly inside Shenzhen, China, over to the end user. Well, in this case, it might end up in a nuclear power plant, and therefore that's why we're most concerned about supply chain risk analysis inside these highly sort of sensitive environments here. Okay. So we have about 2 minutes left. I'll just simply walk us through a pretty quick example here of some essentially traditional, I will call attack chain analysis. So let's just say we have our target facility and we have the reconnaissance phase, and let's look at the chip supply chain. So the storyline goes like this, right? The adversary has compromised a chip during fabrication in Taiwan. The chip contains a hardware backdoor, timing vulnerability that can be triggered by a specific voltage pattern. The backdoor is dormant, waiting to be activated. Now, during system commissioning, the adversary sends test signals to probe which chips respond to the trigger pattern. And in this case, they're mapping which systems contain the compromised hardware. So this is a two-pronged attack, one in the supply chain at the chip manufacturer, where they're implementing the hardware sort of bypass, and then one actually, in field when the system is installed. So this would be a combination of both a attack inside the manufacturing facility, as well as an insider being able to trigger the analysis in the target environment to determine which of the chips actually has this vulnerability or capability in place. So the blind spot here is without comprehensive chip level verification, this particular timing anomaly is going to go undetected. The chip's going to pass your standard functional test. The backdoor remains invisible. So we want to be able to implement that silicon analysis pattern to hopefully detect that this particular type of timing attack or timing trigger has been implemented. Going from reconnaissance, we have now like the weaponization stage, right? And so in weaponization stage now, the compromised chip is part of a control system component. During transport, let's say from Malaysia to Germany, the adversary intercepts the shipment, loads malicious firmware onto the component's memory. The firmware is now designed to activate chip backdoor, exfiltrate system data. Components resealed, continues its journey. So like many of you maybe have seen this, we run an entire class where we teach tamper protection and testing and evaluation against hardware. So when you receive that particular component and it's shrink wrapped and it has the special seals on it, how do you actually start there and then work your way down all the way, as far as you're comfortable into the component itself to ensure that no one actually intercepted and modified it, in transit. In this case, without cryptographic provenance tracking, the firmware substitution is going to go undetected. Manual bill of material review shows component list matches the purchase order. Now, this is going to be a bit of a challenge, right? Because now we have a firmware mismatch, and we might have something in play inside our environment at that level. Again, moving up the chain from weaponization, now we have the payload delivery phase. So the weaponized components now integrated into the reactor's monitoring system. During normal operations, the malicious firmware begins reconnaissance, mapping control system architecture, identifying system safety interfaces, logging operational credentials. Now, the interesting thing here is that, we talked about sort of partners who are like, oh, this is an air-gapped network. These are air-gapped systems. They run on a very sort of limited basis, only talking to each other. So they don't always think about implementing these types of security controls on these systems with the assumption that, hey, no one can touch these. And in reality, of course, is that if you did have a sophisticated implant that turned itself on inside this particular environment, then you would absolutely start seeing these types of, patterns start appearing. And so in this case, it's sort of a fictional scenario, every 72 hours, the firmware sends encrypted status reports to an external command server during routine system telemetry uploads. A very common technique used in order to exfil data is to identify an existing sort of protocol that's used in order to transit data in a trustworthy way, and then just sort of adding yourself to the protocol payload or flipping some flags in the protocol in order to hide your data. Exfiltration is hidden in normal traffic patterns. So in this case, your blind spot is without this behavioral beat. Now, behavioral based on monitoring, the recon activity looks like it's normal system operations, telemetry uploads, but of course it has additional data injected into it. And then finally, we have this effect delivery. So this is stage 4. The adversary has accurate situational awareness from the reconnaissance. They send the trigger command, the chip backdoor activates, malicious firmware injects false data into the safety monitoring displays while sending commands to adjust the reactor parameters. Operators in the control room see just normal readings because they're seeing the normal data because we're sending sort of the normal data. The safety systems receive data showing normal conditions. The actual cooling flow, though, is decreasing. The attack exploits this transitive trust model, monitoring trust components, safety trust monitoring. Therefore, our blind spot is without attack surface enumeration. That particular transitive trust that we really truthfully believe would be enough to identify or protect those systems. Interaction vulnerabilities are ultimately unknown. This multi-layer attack path was never modeled or defended against, and therefore we have a full supply chain inject from component level all the way through to the effect delivery, which essentially moves the reactor into an unsafe state and has the safety systems essentially not ready to respond and interject when they need to. Okay, so last 2 charts is this. We have this idea of, again, traditional test and evaluation. We might do 200 test cases, 40% coverage of the target environment. We might identify 8 issues in 2 weeks. Costs about $50,000 to implement. I mean, anyone who's done T&E knows it's a very timely, costly endeavor. It takes a lot of time. Using this pattern-enabled test and evaluation, we've been able to ramp up the number of test cases that we're able to work against. We're able to have broader coverage against the attack surface. We're able to identify additional issues simply because of the computational gain from the use of the LLM patterns. And then the times of execution goes from 2 weeks to 8 hours, with continuous assessment taking place over time, and also a decrease in estimated cost, although the cost is going to scale based upon the number of weeks or months of implementation. So in the traditional T&E, you're limited based upon manual programmatic test designs, sampling resource constraints limited to known scenarios, very high cost for iteration. And pattern enabled, we can use artificial intelligence generated edge cases, have much broader coverage, actually work against unknown scenarios, and then have continuous execution and cost reduction. So last couple of things, we have some AI generated edge cases here from like error handling, boundary condition, unexpected inputs. We have comprehensive fault injection test cases. We have cross-layer integration testing cases, timing analysis cases, and finally regression testing and continuous execution cycles that all sort of map into this particular pattern-enabled test and evaluation component. And so from that, I leave you with just some final thoughts right here. This is really a layered approach from chip to supply chain provenance, behavioral monitoring, attack surface, and facility-wide assessment. Can we improve the traceability of components through supply chains? Absolutely. Can we improve visibility of supply chain components and human system interaction? 100% through these types of pattern implementations? Can we improve attack surface enumeration across interconnect systems? That's our goal, is to be able to just have a broader view on everything we're doing. We can improve our comprehension on specific risks, not just perceiving the complexity, because every single layer gives us a different view on this. And finally, the real starting point is leadership, being able to invest in the training for staff in order to be able to perform this particular kind of analysis. And so, last chart here, we can perceive complexity, but we can't perceive scale, but we can perceive risk. We need this comprehension view in play. Patterns ultimately bridge these gaps. The frameworks exist, the economics work, the results are real, just a matter of being able to use them. And so with that, I thank you for your time. I ran about 6 minutes over my 30 minutes, so my apologies there. Okay, and I will stop sharing now.
Thank you very much, Chris, for your presentation. It's very interesting, very systemized research and practical framework for cybersecurity analysis for chain-based experience. And so, dear colleagues, we have time for questions and discussion of this very interesting and important topic in cybersecurity and safety. Welcome. Okay, I have first question. You very well systemized hierarchy of risk beginning of chip. My question related to chip level. What is your opinion in point of view such a chain-based analysis? Which risk is more for controller or for FPGA chips?
Okay, so just I want to make sure I heard your question correctly. At the chip level, for chip level analysis, you were asking related to, was it control? Can you just repeat the last sentence? I'm sorry, I think I missed the comparison. What was the, yeah.
I mean, if you talk about FPGA, we have one technology in point of view electronic chips. If you talk about microcontroller or CPU, in this case we talk about software-based decision. Hence, there are risks of vulnerabilities and so on for microprocessor on the level of hardware chip and on the level of software. If you talk about the FPGA, situation some different. Hence, your opinion concerning comparison of these two chips in context of your chain-based analysis.
Okay, I think I understand now. So you're asking related to like FPGAs and more sort of complex chip implementations, right? Okay, perfect. So it's a great question, because we use the STM32 as a base example, right? So the STM32 is probably the most approachable microcontroller that you can examine, right? It's, it costs very little. It's very limited in sort of input output. It has a set design to it. You can perform analysis. Now, compare that to a Xilinx FPGA, right? Or compare that to a system on chip implementation from Apple, have their M2, M3 SoC, right? So an M2, M3 SoC includes not only the CPU, but it also includes, integrated GPUs, integrated memory, integrated pathways. So you have a much different type of analysis that you're going to perform on the system on the FPGA versus the STM32 or the basic integrated circuit. Now, that being said, the analysis patterns we use can be applied to all three of these environments. It's just simply a matter of understanding how they operate. So let's say you're looking at an FPGA. You're looking at the FPGA sort of implementation ecosystem. That's going to start with like your VHDL design, right? So someone's going to load up the VHDL programmer, be able to design out the programming logic they want to be able to apply. They're going to compile it, put it to a bit stream, have the bit stream applied to this device itself, and then you're going to go through the pattern process of being able to validate whether those logic patterns were correctly implemented. So in this case, we're extending from the chip itself, which was fabbed with predefined patterns based upon the design that was at the manufacturer, to a dynamic set of patterns that are applied inside a programming environment that are compiled and applied to the system. Now, as we know, on the FPGAs themselves, many of them have like hardware security modules that prevent you from being able to reflash an FPGA, allegedly, right? A lot of them have the ability to use hardware sort of effects to be able to, like a PUF implementation, right? So this way you're going to be able to take hardware measurements that will align only, hopefully, only to that particular chip, and therefore any sort of variation from that will indicate compromise. So our job now is to be able to say, well, those are the defined security controls that have been implemented inside this particular FPGA or system on chip. Now, the question for us is, A, have they been correctly implemented? B, are there additional side channels that have not been protected that would allow us to perform observability on the chip itself? Because to your point, it's much easier to perform observability on a simple, IC. It's much more challenging to perform observability on an IC that has like billions of, sort of components in play. So this way you have to do one of two things. You either have to come up with a hardware approach that has a higher level of sensitivity, which is going to cost you hundreds of thousands, if not millions of dollars, because that's how much it costs to build out this kind of hardware analysis, or you're going to have to identify mechanisms for performing that out-of-band observability, so that way you can identify, essentially the vulnerability or sort of the function implementation and or vulnerabilities based upon the other analysis patterns, if you will. So I think I maybe answered your question.
Thank you very much for your very extended answer. And okay, please, Artem, listen. Welcome for your question.
Thank you, and thank you for this really interesting report and presentation. Actually, the question about the possibilities. There is a new technology of creation of computations based on the optical elements, like the optical processing that faster than or maybe not spends a lot of the resources during the computations. And even it's possible to create some optical FPGAs also. I'm familiar with FPGA because, it's interesting for me. I mean optical FPGAs. But can we expect then in 10 years there will be some accelerators inside the existing chips, maybe in the same package, with the optical processors or optical components, maybe network optical components directly on chip? Is it realistic, or maybe it maybe will need 20, 30 years, or maybe even early?
Yeah. Obviously, what did we see? We saw optical routers implemented like, 15 to 20 years ago, right? As sort of the evolution from transistor sense hardware digital to optical. In that sense, when we will see the optical inclusions inside the chip space, I think that it's going to be less than 10 years that you're going to see that, especially because our capability design cycles in the past have been limited, I think, based upon, investment inside these particular capabilities. Everyone essentially was investing in known capabilities for deployment, not necessarily those edge capabilities, but it feels now that there is a shift into these edge capabilities that would allow us to see those types of implementations. But it feels like it would be closer less years than 10. I don't think it'll be more.
Okay, thank you.
Okay. Other questions? Welcome, Ahmad Yusuf. Your question?
Hello, Mr. Christopher Spirito. Thank you for your very amazing presentation. I would like to ask from the slides that you mentioned just now, because you said that the hardware backdoor can be implemented on a chip level. Does that mean that the hardware backdoor is being integrated together with the wafer, or it is completely separated from the main silicon, or what? Can you explain for that? Thank you so much.
Yeah. So I'm going to simply offer you this this sort of point is that a lot of people believe that these things are not sort of approachable. But I would refer you back to my point with regards to the so from Slava's question regarding the analysis of particular levels of chips and the type of hardware you would need in order to be able to perform the fabrication, right? So your question's a good one, right? Because the first question would be, are we going to be able to implement this at the wafer or silicon level, right? And the answer there is ultimately going to be, well, it depends upon whether you can gain access to that environment and or be able to swap out that particular component inside of a larger system. And so do these particular implants already exist? And I would argue, there's probably some good evidence that they do. It's just a matter of, how much do you want to be able to invest inside the analysis in your environment of these capabilities? Because the other thing that we often tell our partners is this, like, you don't necessarily have like millions of dollars to invest in supply chain analysis, right? You need to actually choose at some point, like, what you're capable of performing analysis on. So you might simply bound out, that particular type of implant simply because, a nation state or actor who's going to do that is probably already so enriched with capability. That's probably the least of your concerns. Your broader concern in this case is going to be able to identify if that particular capability were to be implemented at that level, what would the actual effect look like when implemented? So in this case, when we talk about air gaps, right? People are like, oh, the air gap could never be, sort of bridged. And I'm like, well, that's fine. You can believe the air gap can't be bridged. But now the question becomes, on the high side or the sensitive side of the air gap, if it were bridged, what do you think you would see? Right? Because once an actor makes their way onto a target device, the set of actions they perform isn't that, sort of mysterious, right? What's the first thing you're going to do on a device that you've actually compromised? Is you're going to perform some sort of set of like surveillance activity in order to determine, where am I? What does this look like? Who can I talk to? What are the relationships that exist? And then be able to move from there into additional layers of effect, delivery or weaponization and sort of delivery effects. So to answer your question, yes, these things likely exist. B, do you care? It really depends upon whether, you have such a highly assured device that you need to care about this. And C, if you do believe they might exist based upon supply chain risk, how can you actually, put a wrapper around it to determine when they might be when the effect will be triggered?
Okay, thank you so much, Dr. Chris.
Thank you.
Okay. I think it will be our last question about component and system level. There are very sophisticated safety critical systems, such as reactor trim system, for example, for nuclear, or onboard control system for planes. And my question is, this system, according with international and national requirements, should be two-version system, main and diverse subsystem, which realize the same function using different hardware software platforms. Hence, my question is, what is your opinion concerning risk in context of cybersecurity for such two-version systems? Because in this case, we have good result in point of view reliability and safety.
Yeah.
What about cybersecurity? Thank you.
Yeah, Yeah, we see that right already in our nuclear safety systems, right, where we have diversity of implementation across the hardware backplane. We have voting protocols that are implemented in order to take common observables and put them into a voting structure in order to be able to then determine whether, X number, whatever your voting percentage is, 2 out of 3 or 3 out of 5 or whatever it is, observable, sort of effects, then they ultimately get ratified as the output of that particular function. So, and again, when I was visiting NewScale, for example, they were showing me their FPGA implementation, which included multiple FPGA vendor types simply for that diversity implementation. Now, is this a good idea? I guess sort of maybe, right? Because if one FPGA ultimately has a vulnerability that is sort of non-remediatable, right? You can't be able to remediate the vulnerability in this. You might be able to then say, well, can I change the weighting on the voting inside the implementation in order to be able to, less weight onto the vulnerable FPGAs, shift them to the FPGAs that don't have the known vulnerabilities. So I think, the challenge you have is a couple, right? One is with every single component that you bring in from a different vendor, you're adding supply chain complexity, right? You need an expert in your environment who is competent on that particular platform. So working with an FPGA on Altera versus Xilinx is not the same, right? It's similar, but it's not necessarily the same. So you would have to make a decision, do I need diversity inside my implementation? Do I need diversity in component level, or do I need sort of multiple pathway diversity in sensor and then, actuator connections? I believe it's ultimately going to be, what you determine as a robust enough solution such that should there be a catastrophic vulnerability or failure of a component, that you don't end up with a system that's non-functional, non-operational. So I think it's, again, we already see this in our architectures. This isn't something that's new. The question ultimately becomes, how does our supply chain analysis affect, how we design this implementation? But I mean, by the way, if you go back to my original point about the anti-pattern analysis, this is the very point. Is that, we believe people make reasonable choices, like completely reasonable choices when it comes to architecture. But we also recognize that when you make a reasonable choice in drawing the architecture and then you actually move to implementation, that's where a lot of the vulnerabilities end up being introduced, because now you've made a reasonable choice on a reasonable technology, but you didn't necessarily understand the entire stack that you're implementing, such that there essentially are latent, vulnerabilities that will appear simply because you weren't aware of them. Yeah.
Thank you very much. I think it's really was last question to Chris. Thank you very much for your very interesting talk, and thank you for interesting discussion for participants, and hope for your new presentation next. Thank you.
Excellent. Thank you very much for having me. I appreciate it. Hope everyone has a great evening. Take care.
Bye.
Okay.
Dear colleagues, we successfully finished the first day of our conference. Tomorrow we will start according with our schedule at 9:30 a.m. According with our program, it will be third plenary session. And one of our section will work in offline mode. And so welcome tomorrow on 9:30. And I ask all moderators to participate in your session and send information about today's session results. Thank you very much, all participants, all moderators, all our presenters.
So could we present the paper if there was issue to be in time for our slot?
Okay, thank you for this question. The procedure is the following. If we need to change some program schedule and move reports to other session, we need to send a letter to me and Professor Nikos Bartis. We will communicate with our moderators to change our schedule. The first point. Second one, if there are not possibility to present your report as exclusion. In this case, we use video presentation, and this video should be sent according with resource, and we will present this video report during session according with our schedule. And I think I answered to your question. Thank you. Thank you. Rule is the following: if presentation if article was not presented, there is a risk including this article into proceeding. Is it rule general? Okay. Any other questions? No. Okay. See you tomorrow, and thank you once more. Technical support for your work. Thank you. Have a good day.